Okay, now we want to start talking about how to get energy out of the nucleus. But before we do that, we need to talk about the two different ways of doing it, which is going to be nuclear fission and then nuclear fusion. In nuclear fission, you're going to begin with a large nucleus. So it's going to be a nucleus that is going to consist of many, many, many protons and many, many, many neutrons in there. And then what's going to happen is it's going to break apart into two smaller nucleuses. And in doing so, it's going to release energy. So all nuclear power plants on Earth today, as of 2024, are nuclear fission power plants. So they're going to take a large nucleus like uranium, and then it's going to break apart into two smaller nucleuses, and these are going to be radioactive, and then it's going to release energy. But the sun does it a different way. So the sun produces energy through nuclear fusion. It fuses things. So in the sun, it starts off with two small nucleuses, and in particular, it's going to be hydrogen. So hydrogen is going to be the raw material inside the sun that is being fused into a larger nucleus. So notice that this is the exact opposite of this one up here. And so it's going to be fused into helium. So that's what our sun is doing even as we speak, and in doing so it generates energy. Now the goal is to have nuclear power plants here on Earth to switch them over to nuclear fusion power plants. And the reason why we want to do this is this does not produce any radioactive waste, whereas nuclear fission does. Also, there is basically an unlimited supply of protons to smash together to turn into helium, because water is H2O, and the hydrogens take off the electron from the hydrogen atoms, and now you've got the hydrogen nucleus, which has a proton in it, and then you could smash those together, turn it into helium, and then the helium we could use in balloons, or we could just release it into the air and it would escape our atmosphere when that happens. So as of now, 2024, there are no nuclear fusion power plants, but there has been a breakthrough in which they have sustained nuclear fusion, and they actually got out more energy from the reaction than they put into the reaction. So the idea is that within another 10 years or so, maybe there will be nuclear fusion power plants on Earth. Now, you might be wondering, this one's a big one, and it turns into two little ones, and this one's two little ones, and it turns into a big one. Where is the halfway point? So, is there an element that is going to be too large to undergo nuclear fusion, but yet it's too small to undergo nuclear fission? Do you think that there's an element like that? And yes, there is. So it turns out that it's the element iron. So a iron nucleus, when you smash it together, you fuse it, it does not produce any energy. And if you take an iron nucleus and you pull it apart, it does not release any energy. And this is going to be really important, especially in stars. So when a star begins to manufacture iron in its nucleus, then that star is going to collapse and violently explode as a supernova. We'll talk about that later. Now, how do we symbolize these two kinds of nuclear reactions? So we're going to do it by using our way of writing isotopes. So do you remember in the isotope we wrote down the element? The lower number was the number of protons, and the upper number was the number of protons plus the number of neutrons. So here is a nuclear fusion reaction. We're going to take hydrogen, smash it into helium, and turn it into lithium. So let's make sure that the numbers work out. So let's look at the upper numbers. 2 plus 2 makes 4. And let's look at the bottom numbers. 1 plus 2 makes 3. And then 3, if you look at in the periodic table of elements, is lithium. So lithium has an atomic number of 3. So let's look at a nuclear fission example. Begin with uranium. So uranium-236, and then all uranium is 92. So it has 92 protons, the atomic number. Okay, that turns into, so that's what the arrow means, krypton plus barium. So let's see if the numbers work out. 236 equals 84 plus 152. And then 92 equals 36 plus 56. So the numbers all work out. So what's it going to look like on the exam? So it says here, solve the following nuclear reaction. So we're starting off with lithium 6,3. We're going to smash it into beryllium 7,4. And we want to know what does it turn into. So you're going to have to fill in the question marks on the exam. So how are we going to do it? So we're going to take the 6 plus the 7 makes 13. We're going to take the two lower numbers. So we're going to take the 3 plus the 4 makes 7. Okay, now we have to determine the identity of the newly formed nucleus. And so we always look at the bottom number because that's the atomic number and that determines the element. So it's a 7. And so we would go to our periodic table of elements. We find the atomic number 7. That turns out to be N for nitrogen. And then we put it in there. Now what about a nuclear fission reaction? So here we're starting with plutonium. And we're going to change it into copper. And we want to know what other element will we create when we do that. Okay, so we're going to, this time, remember that the arrow is like an equal sign. So that we can write it like this, 244, and then instead of the arrow, put equals, okay, and then 64 for the copper, and then plus x. Okay, so from algebra, you know that you can take the 64 over to the other side, and so this is going to be subtraction. So noticed in the previous problem, you added the two numbers, but here you are subtracting the numbers. And so it turns out to be 180. Okay, now let's do the same thing with the bottom number. So that we're going to have a 94, and it's going to be equal to 29, and then plus x. So we're going to take 94 minus 29. That turns out to be 65. Now we've got two numbers, so that we on the top we've got 180, on the bottom we've got 65. Which of those two numbers do you use? Always use the bottom number. So you look that up on your periodic table, which I'll give to you on the exam, and then that turns out to be Tb, which is terbium. So it's terbium. I don't hardly use that word at all. Okay, let's take a break. When we come back, we will talk about, now that we can write the equation, how does that generate the energy in nuclear fusion and nuclear fission.